Thank you for every person coming to my talk, and thank you for invitation. Today I will talk about varieties of general type with small volume. This is a joint work with Professor Burt Totaro. Let's first begin with some background. By Hacon-McKernan and Takayama and Tsuji, they show that for each integer n, positive integer, there exists associated with a constant we called Rn. This constant only depends on integer n. That will be the dimension of the variety we consider. So for any smooth, complex projective variety of general type with dimension n, the map given by the linear system m times the canonical divisor is a birational embedding if m is larger than or equal than this constant Rn, which only depends on the dimension. And the volume of a variety measure the asymptotic growth of the plural general. This is the dimension of the space of sections of the line bundle m times canonical divisor. And if the canonical divisor is ample, we can compute the volume by calculating the intersection number. And also more general, if X is a normal projective variety with adverse canonical singularity and the canonical divisor net, we can also compute the volume by intersection number. And this for all smooth n-fold of general type, and the volume has a positive lower bound, an. We call it an. An is also a constant, only depends on the dimension. And here 1 over Rn to the power n is a bound of it, is a lower bound. And to give a in order to give a classification of algebraic variety, we are interested in finding this constant Rn and an. Then we already know some results in lower dimensional case for an and Rn. Like in dimension 1, we know R1 equals 3, A1 equals 2. And in dimension 2, we know that R2 equals 5 by Boone-Bivry, and A2 equals 1. The extreme cases are obtained by a general hypersurface of degree 10 inside of this weighted projective space. And in dimension 3, we have an inequality of these two constant R3 less than or equal than 57, and A3 larger than or equal than 1 over this big number, which is given by Zhongkai Chen and Meng Chen. The smallest known volume is 1 over 420. This example is given by Janov Fletcher. This variety is obtained by taking a resolution of a weighted projective hypersurface of degree 46. And the linear system induces a birational map embedding if and only if m equals to 23 or m larger than or equal than 27. And in dimension 3, there is an important feature that the volume of the smooth variety of general type may not be an integer because the canonical divisor of the canonical model need not be criterion divisor. And in dimension 4, we know the smallest known volume is a resolution of this projective hypersurface in the weighted projective space with very small volume. It's given by Braun and Kasperk. And in high dimension, the asymptotics of this constant Rn and An are unknown, but we give at least some bounds for these numbers by constructing examples of general type with exotic behavior. And the idea is a much similar as former example that we will take. Resolution of a weighted projective hypersurface with canonical singularities. So this is one of our main results. For every sufficient large positive integer n, there exists a smooth complex projective n-fold of general type with value less than this number. It follows that there exists a smooth complex projective n-fold of general type such that the linear system doesn't induce a birational embedding if the number m is less equal than n to the power log n over 3. This result is built on the idea of former three-person Vatican, Yatali and Thyssen. They found smooth n-fold of general type with value about 1 over n to the power n, and such that the linear system doesn't give a birational embedding for m at most constant times n to the power 2. And our result here actually improve this bound from n to the power n to n to the log n over 3, which grow faster than any polynomials. And our example can also give some information for Noether type inequality. So what's Noether type inequality? In surface cases of general type, surface of general type, we always have this inequality that the value is larger than or equal than a constant times the geometric genus minus a constant. And by Longchen and Zhijiang, for every positive integer n, there exists a pair of constants an and bn, such that the value larger than or equal than the constant times the geometric genus minus another constant for every smooth projective n-fold of general type. And they show this Noether type inequalities can be deduced from lower bounds on the value of lower dimensional varieties. And later, Zhang Kai-Chen, Meng Chen, and Chen Jiang, they strengthened the former example result. They gave optimal result or optimal constants for three-dimensional case. So 3 folds of general type, they prove this inequality and find the 2 constant, which is 4 over 3 and 10 over 3, if the genus is larger than or equal than 3. And these 2 constants are optimal. And in high dimensions, there's no explicit result for these 2 constants. But we can give a bound for it from our result, from our examples. In high dimension, our examples show that the constant an should be very small, like this number, or sufficient large n. So the idea to give this inequalities is a simple approach that we take a product of a given variety with curves of high genus, as suggested by Zhang Kai-Chen and Chengxi Wang. Like for a sufficient large n, we will get a sequence of smooth complex projective n-folds of general type, with genus goes to infinity, and the quotient of the value by the geometric genus is less than this number. Okay. Now let's come to concrete construction of our examples. We need several concepts since we will construct a hypersurface inside a weighted projective space, and then we need well-formed in order to use a junction formula. A weighted projective space is said to be well-formed if we have this graded common divisor equal to 0, if we omit any one of the weights. In other words, we consider the quotient stack am plus 1. This is a fine space of dimension n plus 1 without origin, and that has a group action by this multiplicative group, and the act is given like this. It's related to the weights of the hypersurface, and this quotient stack has trivial. This action has trivial stabilizer group in codimension 1. That's the meaning of the well-formed. Also, you can understand it like there doesn't exist element inside of the group which fix a codimension 1 subspace. So no element, that is equivalent to say no element in the group acts as a reflection element. And we will always assume well-formed. For subvariety inside of projective space is well-formed, this means that we consider the subvariety intersect with the singular locals of the weighted projective space. If this part has codimension at least 2, then we will say it's well-formed, the subvariety well-formed. And here, there's a criterion to check the special subvariety, the codimension 1 hypersurface, a general hypersurface, whether it's well-formed. It's a criterion, and we only need that the graded common divisor if we omit 2 weights of the inside of all the weights. The graded common divisor is divide the degree b. And the second condition means that the hypersurface means that the projective space is well-formed. So from this criterion, we know that if the degree of the hypersurface is multiple of any weights, of all the weights, then the hypersurface is well-formed. Then there's another fact that if we consider the reflexive shift OM associated to a wild divisor for any integer m, then this reflexive shift is line bundle even only if m is a multiple of every weights. This is easy that because if m is multiple of every weight, then we can see that the line bundle is base point free, then it's automatically a line. This reflexive shift is base point free, so it's automatically line bundle. And another thing is we can count computer intersection number of this divisor O1 of this line bundle O1, which equals to 1 of the product of all the weights. Okay, and in order to construct our example, like hypersurface inside a weighted projective space, we hope this hypersurface to have the canonical singularities. So we still have to analysis the singularity inside of the hypersurface and inside of this weighted projective space. So we will use here the Reid-Tai criterion for quotient singularities. For positive integer r, the cyclic quotient singularity of this type 1 over r, a1, an, which means that we have an has an action by the group. This group are the roots of unity, and the action is given like this. Those numbers are here. So we call it this type. Then assume this description is well-formed in the sense that the graded common divisor equals to 1. Then we can give a criterion for whether this cyclic quotient singularity is canonical or not. we just compute for each number I from 1 to r minus 1. And we let this number I time with each weight. And we compute the smallest non-negative residue of the number mod r. And we add all this number together. If the sum is larger than equal than r, then we say that the quotient singularity is canonical. If it's larger than r, we call it, then we can get terminal. And for weighted projective space, things are good that we only have to check the weighted projective space y is canonical terminal at each coordinate points. Then we can get the whole weighted projective space is canonical. This is a lemma given by the former 3-person. A well-formed weighted projective space is canonical, even only for each index m, and instead of 0 to n, we have this inequality. Actually, this is getting from we check the singularity at the coordinate points Pm. That means the m's coordinate is non-zero and other coordinates are 0. So that coordinate points has the singularity of the cyclic singularity of the form 1 over am, and with all the weights just omit am. So use this criterion here. We get this in even only. Okay, now we can come to our construction. This is the basic idea from the former 3-person. They construct the hypersurface of degree D inside of the weighted projective space. Here, K is the weight and the number above it. This means that the weights K will repeat K plus 2 times. Here, the weights K plus 1 will repeat 2K minus 1 times. And so on here, this weight will repeat L times. And we have the degree, which is multiple of the all weights. So we can get the Y that is well formed since K larger than or equal than 2. So we get this number is larger than 1. When we use the definition well formed to compute the graded common divisor, which is always equal to 1. And X is well formed, this hypersurface, because D is multiple always. I have already mentioned the criterion. And we still have to check the canonical singularity using the lemma. Actually, we only have to check 3 different kind of coordinate points. The first one is that we omit one weight from we omit weight K. That's the coordinate points with at the position we have a weight. We have the weight K. At this point, it's a cyclic quotient singularity of this type. And by the lemma, we have to check the sum of all the weights. Sum of I for each I from 1 to K minus 1. We use this I times each of the weights and sum them together. When I times the weights K, mod K, it's always 0. And when I times the K times K plus 1, mod K is always 0. So we don't have to consider those 2 kind of terms. And we only have to look at the term that I times the K plus 1, mod K. And in total, we have a 2K minus 1, those kind of terms. So that's our destination. We have to check this inequality. But it's true that because we have I times K plus 1 equals I mod K. And the similar story for another kind of coordinate points. We just have the coordinates have weights. The coordinates non-zero coordinate has the weights corresponding to the weights k plus 1. And we have to check this inequality, the same similar story as above. And the only terms are I times the k. In total, we have k plus 2 terms. And the third kind of coordinate points, we correspond to the weights k times k plus 1. And this coordinate point has the cyclic quotient singularity of this type. We have to check this inequality using the lemma. This term, we have in total 2k. We have k plus 2, this kind of term, and 2k minus 1, this kind of term. And this inequality is held because we have the I neither the I not divided by k or not divided by k plus 1 for any I from 1 to k times k plus 2 minus 1. If we are in the first case, former case, we use this part. This is larger than or equal than k plus 1. So when we time with 2k minus 1, it's definitely larger than k times k plus 1. If we are in the later case, we use, if we are in this case, we use this part and get the inequality. So we're fine. We get the weight projective spaces canonical, and the hypersurface of degree D is an element inside of the linear system of this line bundle OD, which is base point for a line bundle, since the D is multiple of all weights. Then by Colossus-Bertini theory, we can get X as canonical. And we still need another concept that's called quasi-smooth, because our destination is to compute the volume. And in order to compute the volume, we want to know the Cartier divisor. And quasi-smooth and the well-formed together allow us to use the junction formula. So we have to mention what is quasi-smooth. A closed sub-variety is called quasi-smooth if it's a fine cone is smooth outside the origin. And here, this is a lemma given by Jan Fletcher. We can check the quasi-smooth. The first case is that there is a weight equals to the degree. And the other case, if this doesn't satisfy it, we can check for whether it is satisfied that for every non-empty set of the index 0 to n, we will have neither the degree D is a n linear combination of the numbers ai with the index inside of the set I. Here n is a natural number, or that there exists a number j, index j, which doesn't belong to the set I, such that D minus aj is a linear combination of the numbers ai, with index I inside of I. And we need those kind of number. We need those kind of number j, those kind of index j. The numbers of those kind of j is equals to the length of the set I. That's a criterion for check the quasi-smooth. And from the definition, from this criterion, we know that if the degree D is multiple of all weights, then 2A is satisfied. D is always a linear combination of the numbers AI. So when D is multiple of all weights, then it's quasi-smooth. Okay, let's come back to our example. This example constructed by former 3-person. We have well-formed quasi-smooth since D is multiple of all weights. Then we can use a junction formula. that the canonical divisor is the OX D minus sum of all weights. And we get this number equals to the positive number 1. Here, this is the ample divisor. So we can compute the value by calculating the intersection number, which is the degree D divide by the product of all the weights. Then we take the resolution of the singularity of X. We get W. W is a smooth complex projective n-fold of general type with value equals to the value of X, since X has canonical singularity, so the value is invariant. Then we generalize this idea. We can consider the trick is here. The trick is that we should properly choose this number such that we will get the weights, get this D minus sum of the weights equals to a positive number 1. That's the trick here. And we generalize it. We consider 3 consecutive integers, k plus 1, k plus 2, inside of the this weighted per degree D hypersurface inside of the weighted projective space. We have weights 1 and k plus 1 and k plus 2, and so on. And here that means the weights 1 repeats 3k plus 2 times, and so on. And in this case, we also can get similar idea. We can get Y is well formed since 1 occurs more than once. And X is weighted project well formed and quasi-smooth since the degree is multiple of all weights. And also we can check, use the lemma at each coordinate points. We can get canonical. Y is canonical, and also with the Bertini theory, cross Bertini theory, we get X is canonical. Then we use the adjunction formula to compute the canonical divisor. So the things here is we have to properly choose those numbers such that we will let this difference equals to 1. The value equals to the degree over the product of all weights. You can see that here the denominator is larger. This actually improves the former person's result example. Then we further generalize it. We can consider B consecutive numbers of consecutive integers from k to k plus 1, and so on to k plus b minus 1. Those are our weights. We will consider those kind of weights. The question is how to choose this number. Then we properly choose the things. The number depends on the size of the index. Now we can get the we can also compute the canonical divisor using the adjunction formula, which also equals to 1. And if we take sufficient large dimension, it allows us to make a simple choice of the parameter b and k. Then we can get a upper bound for this value. That's the conclusion. And a similar idea and a similar construction can give us result in other cases that terminal funnel varieties. We have for terminal funnel varieties, the former result, some background are we know that for each integer, and they're also associated with a constant Sn, such that the m times anti-canonical divisor give a birational embedding, or m larger than equal Sn for terminal funnel n-fold. And we also have a lower bound for this volume and canonical divisor. In lower dimension, there are some results. Like in dimension 2, we get optimal cases, which is the hypersurface of degree D with volume 1. And in dimension 3, we have a volume 1/330. And in dimension 4, Brown and Kasper's example, this is a hypersurface with very small volume. This is the best terminal funnel fourfold known so far. Like in higher dimension, and some topics of this optimal constant are unknown, but we give examples. Use weighted projective space. We only have to choose the weighted projectives that we use above to add 2 more weights equal to 1. Then we can get our example. In high dimension, for every sufficient large positive n, there exists complex terminal funnel unfold with the volume of the anti-canonical divisor less than 1, less than this number. And it follows that the linear system doesn't give a birational embedding if the number m is less than or equal than n to the power log n over 3. Those are for terminal funnel unfold. And note that such exotic behavior is not expected for smooth funnel varieties, because Fujita's conjecture tells us that for every smooth complex projective variety, x of dimension n with ample line bundle A, we have kx plus n plus 2 times A is very ample. If we choose this A to be here, minus kx is equals to 0,1 in the example, then we can get this n minus 1 times minus kx is already very ample. Okay, that's our that's the second result. And more for comparison, we consider some other things with weakened assumption. We can consider a PAL that is a variety with a divisor, Q divisor of it, and consider the KLT variety. Here is some background. Clause proposed that what may be the KLT PAL general type with standard coefficients that has minimum volume. General type, that means that the canonical divisor kx plus the Q divisor is big. Standard coefficients means that all the coefficients of the Q divisor delta are of the form 1 minus 1 over m, or a number m inside of the positive integer. So that means the coefficients are some non-negative rational numbers less than 1. And the volume, there is some positive lower bound for such volume. The minimum is obtained, and the volume satisfies the descending chain condition by Hacon-McKernan and Shi. This is the example that we reach the minimal volume. We consider the projective space. Here, HI are the hypersurface. And the constant number CI are inside the silver sequence. The silver sequence have a first term equals 2, and the other terms are given by this recurrence relation. And the volume of kx plus delta is very small. And the optimality of the Collas example is known only in dimension 1 which is the Hurwitz orbifold of volume 1/42. And in surface case, we already know some results. For surface case with ample canonical class, the smallest known volume is this number by an example of Alexander Liu. In high dimension, we get, this is another result in our research, we get for every integer larger than or equal than 2, a complex KLT n-fold with ample canonical class, such that we have the volume less than 1 to the power 2 to the 2n, 2 to the power n. And our KLT variety with ample canonical class should be close to optimal in high dimensions. And here you can see that the log of the volume of the canonical divisor of our variety is asymptotic to the log of the volume of the pair. Kx plus delta in plus KLT pair when n goes to infinity. The details of our construction are intricate, of our example are intricate. We will combine several sequence and also several sequence of polynomials defined by recurrence relations. Here is our result, our construction of the example. We construct the KLT varieties with ample canonical class. It's also construct in a hypersurface inside of weighted projective space. And I will tell you how to choose these weights and the conclusion we get. Then I will say why we choose these weights like that. We will use the serial sequence to define the weights. Let n larger and equal than 2. We denote y is Cn minus 1 minus 1. This number is inside of the serial sequence. And the first 3 weights, A0, A1, A2. A2 is a polynomial of y. A1 is also a polynomial y, also related to the A2. And A0 is also a polynomial of y, which is related to A1 and A2. This is the first 3 weights, and we also have to define the weights with index larger than or equal than 3. We let the number x equals to 1 plus the sum of first 3 weights, and the degree here equals to y times x, which is the product of the first several terms inside of the serial sequence and time with x, which is also a polynomial of y. And we define the weights sorry, divide the weights with index larger than or equal than 3. It's like this. You can see that b over ai plus 3 actually equals ci. So ai plus 3 is divided d. Later I will tell you why I choose these weights like this. And the conclusion we get is x is a general hypersurface of degree d inside a weighted projective space. And the x is KLT. Then we can get x is a KLT variety with dimension n and the ample line bundle, ample canonical divisor. And the volume is equals to the degree over the product of all weights. Then we can compute it like this. And then we have a bound for this volume. Okay, this volume should be fairly close to optimal. It's about 7/8 power of the volume class conjectured optimal KLT pair. Since here we have a 8n, 1 over Cn minus 1 to the power 18. And here on the power is 7n minus 1. They're very close. Okay, this here I will explain why we choose these weights. By some example with very small volume, we find that especially the biggest weights, several weights are actually divide the degree, and our ratios are close to several sequence. So we so we let D over AI plus 3 equals to CI, like inside of our definition here. And we know that we can assume D equals to some number, those numbers, time with another integer. And now the question is how to choose this integer. Then our ideas, we find if we want to let them use the junction formula and compute the D minus sum of all weights equals to 1, then we will get it's equal to 1 if only if x equals to this number. Okay, then the next question is how to choose the first 3 weights. We will need this hypersurface to be quasi-smooth so that we can use the junction formula. And now we will use a sufficient condition instead of the criterion. For quasi-smooth, we consider for positive integer D and some other integer. A general hypersurface of degree D inside of the weighted projective space is quasi-smooth if D is larger than equal than any weights, and also satisfy another 2 condition. There is a positive integer R such that we will have all the weights except for the first R weights. All but the first R weights divide D. And how about the first R weights? They satisfy a circle of congruence. If we have this 2 condition, then we can see that this hypersurface is well smooth. So use this sufficient condition. We choose the other weights A0, A1, and in the former example, we choose the former 3 weights A0, A1, and A2 to make X to be quasi-smooth. They satisfy a circle of congruence. And that's the reason how we define the in the statement of theory, how to choose this A1, A2, and A0. And our construction can give those examples. In dimension 2, we get hypersurface inside a weighted projective space with volume 3.5 times 10 to the power minus 5. And in dimension 3, we have this weighted hypersurface with volume 10 to the power minus 16. In dimension 4, we have the example with volume 1.4 times 10 to the power minus 44. And the smallest known volume for KLT fourfold with ample canonical class is about 1.4 times 10 to the minus 47. Look at this number, they're much closer. I will skip the sketch of the proof and come to, I want to compare that number with a better example. We generalize our idea to better KLT varieties with ample canonical class. For any odd number R larger than equal than 3, we can construct variety with dimension n larger than equal r minus 1. Actually, r is the index when we construct an example. More details you can see in the paper. And we construct a weighted hypersurface inside a weighted projective space, and the weights. First the set R weight has satisfy a circle congruence. And for that is better result, better example because we can choose R more large. In the former example, actually R equals 3. We just consider A0, A1, and A2. They satisfy the circle of congruence. And for the better example, we can get the actually the value is close to optimal in high dimension. We have this quotient, compare the log of the value of our canonical divisor of our example, and with that one, that's the pal in Collas KLT pal. They goes to this number when the dimension goes to infinity. And for r equals 3, this is the former example. When r equals 5, we consider dimension equals 4, we construct the example, which is 10 to the power minus 45. And you can compare this number with former one here, minus 47. You will see that it's better than minus 44. That's our better examples. And the sketch of the proof, I will see very quickly. We just have to construct that. Here I just repeat the weights definition of all the weights. And we want to prove this X is quasi-smooth in the well form. We know it's KLT since it's only have a cyclic quotient singularity, and it's quasi-smooth since we have used the sufficient condition. Then quasi-smooth in the well form, we can use the junction formula to calculate the volume. And when n goes larger and larger, this number inside of Silver sequence get larger, which implies y get larger. So when n is very large, we can see that the major parts are y to the power 3. So we can get we can see this inequality for this weights A2, A1, and A0. They are polynomials of y, and x is also polynomial. So we get the inequality. And use some result use the factor of Silver sequence, we can get the root statement of the volume. Okay. So that's the sketch. Then we can get the generalized idea to get better results.